In this section, we're going to look at voltaic cells or galvanic cells. Either name applies. This is basically a spontaneous redox reaction designed to create electricity. In this section, we're only going to focus on the parts of the voltaic cell, and in later sections, we'll talk about how to calculate the energy of those cells. So the reason why we care about these redox reactions is because you can use them to make a voltaic cell. Basically, we are going to channel electrons from one piece of metal, which is oxidizing, to another piece of metal that is being produced. And that electron movement, which will create work, is essentially a battery. Okay, so what we have is an anode, which is where oxidation will take place, and a cathode, which is where reduction will take place. And I remember that from the vowel consonant rule. So oxidation is anode, reduction is cathode. What we're going to have happen is we're going to have a bunch of zinc metal, and we're going to have a bunch of copper ions. So the copper is reduced, and zinc is oxidized, and the electrons will travel through this electronic wire. Now, the movement of those electrons in the spontaneous forward direction creates work. And we can move then electrons through an electronic device, and that essentially creates a circuit, which gives us energy. Now, the other thing we have here is a salt bridge. And this salt bridge here is here to balance the positive and negative charges. It turns out, over the course of time, this anode is going to get more and more positive from the zinc ions, and this cathode is going to get less and less positive because it's losing copper ions. And so what we're going to do is add a bridge with a bunch of ions. It could be really any set of ions. We typically use sodium nitrate because they're very, very soluble. And so as the cathode gets more positive, gets less positive, we're going to add in sodium positive ions. As the anode gets more positive, we're going to add in the NO3 minus ions, and that is going to balance the charge and allow this reaction to proceed as smoothly as possible. Now, typically when we write a voltaic cell, we write it in this format up in the upper right-hand corner: zinc/zinc 2 plus, / copper 2 plus, copper. So the way to think about this is that these two cells are physically separated except for the wire and the salt bridge, so that's the double line. And then we have a zinc 2 plus anode, and we're always going forward, a copper 2 plus to copper cathode, and you can tell because we're putting the arrow forward. Now, typically the anode is written on the left and the cathode is written on the right, but that's not always the case, so do make sure you read, and I would write out these equations, balance them, and then write them into the overall equation. It's worth mentioning that you will see changes in this as the reaction goes forward. In this reaction where we have an anode, what you're going to have is electrons leaving the zinc, and so you're going to see the zinc whittle away as the metal becomes zinc ions. On the other hand, because electrons are being supplied into the copper, what we're going to see is that the copper slowly add on, and this cathode is going to get larger and larger throughout the course of this reaction. All right, so one of the things we want to make sure we can do is identify the cathode and the anode and what is where. So this is an extremely crude picture of a voltaic cell, but it works well enough. Figure out where each metal will go in this picture. So look above and see if you can figure out what is being oxidized and what's being reduced. Okay, so if we look at this picture, manganese +2 is going to manganese, so it's clearly being reduced over the course of the reaction, so that will go on the side where electrons are moving towards. On the other hand, as lead is getting positive, so that is being oxidized, so that will be on the left side. Now keep in mind, I could pretty easily just change the direction of the electrons, but the cathode is always going to be the side that electrons are moving towards. In this version of the voltaic cell, we're going to look at this voltaic cell through the half-cell method. So look at this half cell setup, figure out which of these reactions is being oxidized, which is being reduced, and then place those chemicals in the correct voltaic cell. So if we break this down into two half cells, we have aluminum going to the aluminum ion. Remember, this is always going from left to right. So we have silver going to the silver ion. So that's got to be our oxidation. Therefore, that is in the position that is losing electrons, so oxidized. Copper, on the other hand, is being reduced, right? It's getting more negative, and so therefore it is gaining electrons. So the copper metal and the copper ion on the right-hand side, aluminum metal and aluminum ion on the left-hand side.